Good evening, ladies and gentlemen. This is the last video covering the brief tutorials on the simulation workflow of discussing kind of how to think about setting up your own configuration inputs while using SCoBi SCoBi. So for our final one, we're going to be looking at another P-band antenna, another P-band signal of opportunity transmitter, and we're going to be doing a root zone simulation in which we're not just representing our solar moisture profile as one block. We don't quite know what it is, so we're going to try to write for that. Okay, so again, this is a root zone analysis over bare soil. And we're going to assume, for simplicity's sake, that we have a geostationary transmitter. The antenna is going to be a generalized Gaussian antenna pattern, and we will be looking at things in a time series mode, so this is different from the last ones. And again, this is multi-layered because of this being a root zone analysis. Okay, so let's look right into our configuration input files. So the keywords that are going to spice up the configuration inputs file here are the simulation mode is time series, so this is new. The transmitter orientation is geostationary, and the ground structure is multi-layered. So let's take a look at the configuration inputs files for a default time series multi-layer transmitter that is geostationary. You can see that all of these files have a naming convention that kind of indicate what they are, so feel free to check those out if you are curious. So this is the one that we're interested in for this sort of simulation. Okay, so again, as stated before, the order of these sheets matter, but the names don't. The first sheet is going to be for our variables that change, that vary. Okay, so since we declared that this was a time series simulation, our very first column now has to be our function of time, and this is indicated by the day of year. So what this value shows, this is the 123rd day of year. I think you can use a function in Excel to get that, but let me see here, maybe if I put in 123.75, something like May 3rd is what that kind of corresponds to. I don't know if that's exactly right, but anyway, so that's roughly in May what this shows. At 0.75, that indicates that it's at 3/4 of the way through the day, so that's 6 p.m. Okay, so the variable for day, year, I'm not necessarily sure if it has to, the variable for controlling the time, I'm not sure if it necessarily has to be in terms of day, year, but I do think it has to be an integer value, so keep that in mind. Alright, so one thing to note is that in our problem definition, we said this is a geostationary satellite, and up to this point, for our examples, we've assumed that we had a variable antenna orientation. And if that was the case for this one, we would have two columns right here, which would have been theta and phi, and we would have had some numbers go corresponding all the way down to the bottom of this page. Sorry, where these variables stop. But we don't have that because, again, this is a geostationary satellite in this case. The RMS height is a constant 2.5 centimeters throughout this, and we can list that just by writing the single RMS height value right there. And the final values, the final columns that we see here, are the volumetric soil moisture values at different locations, at different depths. These values are declared in the ground sheet and are filled out. I apologize, I got the yawns. Okay, And these values are filled out in the dynamic sheet. So let's take a look at the ground sheet. Now, the name, again, of these values can be arbitrary. You could have just filled these with nonsense text and things would be fine. But the layer depth is a function of meters. Since this is 0.05, the first column shows that this is 0.05 by saying it's the volumetric soil moisture at 5 centimeters, or 0.05 meters. So these values are shown right here. So these correspond to the 4 columns that we were showing on the previous page. And for each of these values, we indicate the sand and clay ratio, as well as the bulk density for each of these different depths. Now, the last few variables here, del Z is the layer, I believe this is how you say it, discretization of each of these different layers. So this corresponds to 1 millimeter discretization. And what that means is that, well, I'll get into what that means in just a second. ZA indicates the thickness of our air layer, and ZB indicates the layer of the thickness of our bottom layer. So if we take a look at what we have here, we have ZA, ZB, and these values right here. So if we were to kind of draw this guy out, that means that our air layer is going to be 0.1 meters or 10 centimeters. We have, let me go back to that page. Then we have our soil moisture profile, and that's going to go from from 0 down to 0.4 plus 0.3. So in other words, that is going to be 70 centimeters, because that is 4 plus 3, 70 centimeters. All right, and the layer discretization will calculate the effective dielectric every 1 millimeter all the way up this soil moisture profile. And it does that by calculating the dielectric based on some function fits that are defined in the GUI window. So essentially, for every point on here, we will have some sort of function that will, as a function of depth, I believe that's good. And if I have the volumetric soil moisture here, we'll have some sort of function that will define the soil moisture as some sort of function fit down the whole depth. And that's how we're going to calculate the dielectric values every 1 millimeter for this profile. Okay, so that does it for this. That is the inputs for a multi-layer time series input. So again, to recap, since this is a time series, we add in 1 column at the front. Since it's a geostationary satellite, we take away those 2 columns that define our theta and phi value, and we just carry on with our RMS height. And then since it's a multi-layer, instead of being 1 column that defines our effective volumetric soil moisture, we now define the volumetric soil moisture in every point that's defined here in the ground spreadsheet. Since these were 4 points, we had 4 columns that define our volumetric soil moisture at these points. And this corresponds to what could be a real-life example where you are monitoring the soil moisture at these different depths. Okay. So, since this is a bare soil study, we don't have any vegetation canopy. There's nothing to model. There's no cylinders, there's no discs, no branches, no leaves. We don't have to worry about that file. And again, since this is a generalized Gaussian antenna pattern, we don't have to worry about creating one of those either. So we can just go straight into running SCoBi, selecting the root zone, and again, name the campaign something to the effect that you want. This is a time series, bare soil. Select these values to your liking. 370 megahertz antenna to make it P-band. Range to Earth is good. Change this value if it works for your problem. Polarization is whatever it needs to be for you. This is important. This makes sure that we don't have to add in those theta and phi columns into our configuration inputs file. And this is our constant look angle for our new geostationary satellite. Okay, so this is also important. Well, again, choose whatever dielectric function that you prefer for this to calculate your soil moisture dielectric. But to estimate the volumetric soil moisture at each of those layer discretizations, which, as we showed earlier, was 1 millimeter for this problem because that's what we typed. These are our 4 different fits, and currently we have 1, 2, 3 checked. We have discrete slab, logistic regression, and second order polynomial fit checked. If you want, you could add in the third order polynomial fit, but you don't have to. And finally, a receiver pattern. So all this checks out. This is, whatever your receiver antenna needs to be for your problem. We've discussed this a couple of times. And again, generalized Gaussian pattern stuff, that hasn't changed either. So altogether, those are all of the variables that you need to do to cover the problem that was defined in this one. Okay, so overall, we've gone over how to set up a snapshot simulation mode and how it affects your configuration inputs file. We've shown how changing ground cover will affect your vegetation inputs file. We've shown how the orientation affects your configuration inputs file, and how the ground structure also affects your configuration inputs file, and how checking the antenna pattern will possibly set up your antenna pattern file. So with all that in mind, you should be good to kind of play around with these different configurations and hopefully have fun with all that. So thanks for watching, friends.